we had this strong Markov property. So I sort of, we discussed that a bit last time, then we applied it to prove the law of large numbers for Markov chains. And that's a pretty mysterious looking thing, I know. And remember, what this means is, if H is, we're talking about a function on sequences, and that theta tau is just shifting the elements again. So it's similar to like all this stuff. I mean, look how hard it is to write that down, Really, we're just trying to get some compact notation, so we don't fill up a whiteboard in one, it's just in the first 5 minutes of a lecture. It's really a trivial notation, right? You're just, shifting time, basically. But this is a really powerful result. It's used all the time, okay? And this is just, and what is that? So for any initial condition x, I can compute an expectation, all right? So I compute that for every initial condition. I get a function on the state space, and then I evaluated x equals a random state. The state at sample at time tau, So there's two steps there, There's this mysterious expectation of a random variable, and then you do that for every initial condition, consider that a function of x and plug in x of tau. So there's two weird abstractions there, but it turns out to be really useful. And again, in particular, it's how you prove the central limit theorem and law of large numbers. It's one way at least. And so last time so that was one thing. Okay, so when I write c of x, it's going to be a cost function, and we're going to often be interested in the steady state average cost. It'll be something we want to minimize. And so I often use eta for that is shorthand, or pi of c, meaning like a dot product, which is what I mean right there. So it's a steady state mean. And so we got a really cool result. So based on looking at blocks, by considering IID blocks. All right, so we basically looked at subsequent times at which we revisit some special state x dot. So again, we've got time going this way, the state space is going that way, maybe it's the integers or something. And there's some special state we decided to identify called x a bullet. you know, and we start off here, and we keep crossing that. We keep crossing this, meeting this special state over and over again. So this was the first time, and there's a second one, and so forth. And so we're summing the cost over subsequent intervals. And those turned out, we proved that those were independent, identically distributed. I gave almost a complete proof, and I sent out notes yesterday. The only change right here is I realized I should not be using G as I did last lecture, because C, C, C will be the cost functions we consider. So I changed the G to a C. So that's the only difference. So, all right, so basically, I want to look at this a little bit more today. So I want to go in, because simulation is going to be important in this class, and say a little bit more about what this means. So the first half of this, first hour of this lecture will really be how-to for doing simulation, because you're going to want to be able to estimate performance. And I know you all need this looking at the homework. You need to be able to think more deeply about how to estimate the mean of a, estimate that. All right. So what we see from this is that if I wanted to estimate this this quantity eta, I would define eta, say hat, and my estimate just to be the average. And you would all plot this, and you'd say, "I'm done." And I've seen your homework, so I know that's what you do. And is there a red pen somewhere? No way, That's a mistake, is to look at a single trajectory, say, oh, it's settled down, I've converged. I will give you examples where you're off by where the actual eta is over here, okay? It's just really not right, okay? For Monte Carlo, maybe it's a little bit more okay to do that, but no way. In general, it's not. So the big question of when to stop is a big question. So two questions, actually. Well, boil it down to this: bias and variance. So let's just stop the math for a bit and just think about how you would really try to get a handle on this. So bias is pretty easy, I think. There's my estimator. Take the expectation and to get the bias. Oh yeah. Sorry. So by definition, the bias is the expected error. So I've got the estimator at time n minus the thing that I want it to be. I'd like this to be 0. That'd be no bias, right? And what's the expectation of that, everybody? I mean, it's the expectation. It's 1 over n, some k equals 0 to n. And I could write it as the expectation of c tilde of xk. Remember I told you last lecture, whenever you see a tilde, I'm looking at deviations. Okay? All right. Because the average of eta is eta, and the average of c of xk is what you've got up there. All right. Now, doesn't that look kind of familiar? Do you remember we played around with these sums before? So basically Poisson's equation can be written this way. you know. And I remember we fooled around with iterating this thing, you know. So p squared h equals ph minus pc tilde. All right. And what's pH? Well, we just said it's h minus c tilde. And I go back to your notes. I said by pattern recognition or by induction, however you want to put it, p to the nh is equal to h minus this sum. And does anybody see the connection between that and that, you know? This is a thing that I'm asking you to go and review before you go to bed every night. Right? You know, p to the kc tilde is the expectation, you know. I should put a little x there maybe, you know, because it depends on the initial condition. I don't know, so I'll write this out. So the expectation of h of xn given x0 equals x, that's a thing that you have to read every night before you go to bed. You know, I mean, really, really, and in homework, as of homework 2, only half of you have done that. You know that when I write p to the nh, I mean the conditional mean, right? And that's equal to h. Now I'm going to get evaluated x minus, and that's just this. Cool. Are you with me? And so then I can divide by n. And I have this sweet formula. So you get that that's the bias, right? Because I can take the sum inside. What I did no, it's the same thing, right? I don't see any difference. So the bias at state x, starting from initial condition x, is equal to, bring this over to the left and that to the right, it's h of x over n minus that over n. So I could write this as equal to 1 over n times h of x, and I don't need this crap, I'll just write p to the n again. I mean, putting this longhand does not need it. All right? All right, so we see the bias goes to 0 like 1 over n typically. I mean, typically like a finite state space. This is just some bounded thing, and it's going to converge to a steady state mean under these ergodicity results I talked about before, geometrically fast. And we might as well assume h has 0 mean. You can do that. So this goes to 0 geometrically fast. So then everything's determined by that, So bias goes to 0 like 1 over n typically. On a countable state space, I could give you an example where this blows up. This might blow up like square root of n, and the bias goes to 0 like 1 over square root of n. It would take me a lot of time to cook that up. I know I could do it. Forget it, finite state spaces, reasonable assumptions. This thing here is bounded, and everything's okay. All right, so that's the bias, and so that's fast. 1 over n is fast. You have a million samples, 1 over a million is small. All right.
So just to clarify, that should be n minus 1, right? Bias.
Oh, where?
No, the bias on the.
No. Look at my definition goes to n minus 1.
Yeah. So that should be n minus 1. Right?
Where?
Just under 2 questions.
Oh, you're right. Here's a typo. Yeah. Okay. All right, so anyway, there's the bias. What about the variance? So in terms of variance, basically what you do is this. We know that this error, where is it? The bias. Yeah, so we know the difference goes to 0 almost surely. And what you can do is you can crank things up. Do I have a hat there? Yeah. So this is what any statistician does. They have this thing going to 0 with n, and they hope the central limit theorem holds. All right? That this goes in distribution to a n0, and I'm going to use gamma squared c as n goes to infinity. And I'll explain what I mean. What I mean by this, so this goes to 0 almost surely. All right? So what I'm doing is I'm multiplying by something that blows up and hoping that I get convergence to some random variable. And again, what this means is, because that's a Gaussian, it just means that if I look at let's give this a name. Let's call it Wn. All right? So this means that the probability that Wn is greater than or equal to some r, any scalar r you want, converges to the probability that gamma c times w is greater or equal to r, as n goes to infinity, where w is what? Where w is a Gaussian standard random variable. All right, now, nothing converges really. It's only the distributions that converge. I have this crazy random thing, and it's not converging, it's bouncing all over the place. But if I look at its distribution, so I'm looking here at its, what is this? This is the complementary CDF. It doesn't matter. I could have put a less than. If I look at its, its CDF, the CDFs converge as n goes to infinity, just something identifiable Gaussian. And so heuristically, I should put this in parentheses. So this is the kind of thing that you'd write down. Basically, saying this Wn converges in distribution to an n01 random variable, and I forgot something, didn't I? Forgot the gamma. All right. Okay, so this has to be, again, thought of really carefully. There is no W you could plug in there. Again, this doesn't converge. If you plot this as a function of n, you'll just see noise. It'll just be bouncing all over the place. All right. But this difference, scaled by square root of n, will, it has a Gaussian distribution. The way you'd see this is by repeated experiments. So you'd do an experiment. Find eta hat n for n equals 1,000,000, right? And you get one sample. And then you do an independent run for 1,000,000 steps, get another sample. Do it again for 1,000,000 samples, Then take the difference, scale by square root of n, and you'll get a histogram, and you'll get a Gaussian,
So why scaled by a square root of the n?
Yeah, why is that? It's right there. So the question is y squared of n. Let's see if we can think about that. So I can kill this, right? Well, y squared of n, I mean, think about the ID case. Suppose that Zn, actually, I shouldn't call it Zn, I should call it Bn, because that's been used. No, that's confusing. All right. Suppose I have an ID sequence. Its mean I'm calling nu, and its second moment is finite. And as we all know, the second moment is the variance plus the mean squared. So nu is just a symbol for the mean, and we have that. All right. Then if I look at the averages, if I look at the expectation of 1 over n, sum from 1 to n, of Zn minus nu, quantity squared, so that's like my bias squared. All right. Right here I've got the bias, and so. But here, I have a Markov chain. That is not IID, so it's, it's a special case. So the beautiful thing about IID is that if I go through and square this out, I get all these cross terms. But these guys are uncorrelated. The Zn minus its mean has 0 mean, and the independents, they all cancel each other out. So what I end up getting is, you do the work. The 1 over n comes out, you get 1 over n squared, and then you get a sum. Oh, I put a there, sorry, k. Sum k equals 1 to n. And so all of these are just the variance. So I get n variance terms divided by n squared. All right. So the question is why multiply by the square root of n? It's because if I want to create something bounded here, I would just multiply by n everywhere. It's the right normalization to make it bounded. So I take the bias, I square it, and I take the mean. If I multiply by n, I just get the variance. Now that's for IID. Okay, so the hope is you can extend this result from IID to, and also it's known also that if I take the bias and scale it by square root of n, that does go in distribution to n 0 sigma squared. All right. Okay. Now, so why would IID come up? Remember last lecture, the way I proved the law of large numbers was by reducing it to a sequence of IID terms. All right. So one way to prove this central limit theorem for a Markov chain is to again look at these IID blocks, apply the central limit theorem for the sequence of IID blocks, which is right there, So take the Zn's to be these, block n, and then translate the central limit theorem for the blocks to a central limit theorem for the original thing you care about. All right, and that can be done. I won't do it. Okay, so I can give you references. I'll state what you get from that. And it gives you this really cool formula for the variance. Like that. So when you go through this work, you go through and you say, well, the CLT holds for the average of these blocks, and then you somehow translate it back. You end up getting a formula, which is you get the ordinary variance of a block, and you end up scaling it by this. And that's because of the fact that we're dividing by the wrong things. When we look at the central limit theorem for the blocks, we end up dividing by n. After n blocks, but n blocks corresponds to visiting this special state n times. Okay, so you have to fix that mess up with sampling, So that's how you get this small scaling factor. All right? That's a pretty worthless formula. I mean, it's intuitive, in a way, once you internalize this IID analysis. But in terms of trying to get an idea of the bias, how would you get a grip on this? How would you bound it, to get some idea of when to stop? All right. Cool. All right. So, all right. Any questions? Yeah. I mean, I don't expect you to see this. It would take a long time to go and derive the CLT and get this variance. I'm giving you the facts. I'll give you references if you want. Now, the standard approach. I mentioned this already. So what I mean by the standard representation is if you take a stochastic processes course and they tell you they'd like to prove the central limit theorem for just a general stationary process. This is not about Markov chains, it's about any stationary process. It turns out if the central limit theorem holds, very typically it's the sum of the autocorrelation. All right? So I take the Markov chain, I initialize it with the steady state distribution pi. That's what that means. That E sub pi means my initial state is not, I'm not fixing some initial state, I'm randomly choosing according to pi. And then looking at this autocorrelation, and there's a definition. I'm summing from minus infinity to infinity, so if we're going backwards in time, I just have symmetry like that. All right? So that's something you can find in textbooks. You pick up a book on the CLT for non-ID processes, that's what you get right away. All right. Now, how do we relate this to our other friends? Now, you see there's a conditional expectation in here, right? Anybody see a conditional expectation? And you see a sum. A light bulb should be going off. So what is this term? Let's compute it. Okay, so if you didn't know what I meant by this, now you do. Okay, I look at all possible values of x0 equals x, and I take the probability pi of x, and I sum. Okay, that's what I mean. Okay? Yep. Now, if I'm given x0 equals x, then I sure don't have a random quantity here. I can take it outside. Now, please, somebody tell me what this is in my notation. It's a conditional expectation of a function of a... Yeah. Equal.
Sorry.
Yeah, too slow. How about you? No? Okay. So it's some here in the board already, isn't it? Anyway, that's p to the n, you know? Okay, you... Cool. So this thing here is given by just this funny dot product here, okay? And then I'm going to sum over all n. Well, get this. What can I kill? Yeah. If I sum this monster now from 0 to infinity, what do I get? You know, it's given right there. I know that's not what I want. I want to go from minus infinity to infinity. But let's do this first. So I get a sum over x, p to the n, c tilde at x, c tilde of x, pi of x, and I can swap these typically, okay, you know, as long as it's all, this sum exists. If I can put absolute value signs there and get something finite, it exists. I can swap. There's actually a name for this. It's Fubini's theorem. You know, the fact that you can swap sums, it requires assumptions, but I'll just take it for granted. And does anybody know what this is? Does that have a name? Well, let's call it something. Let's call it psi. A beautiful psi. That's supposed to be flowery, okay? It's a grand letter. And what would happen if I hit it by p, everybody? Sounds like the homework, doesn't it? All right, p times p to the n is p to the n plus 1. And that looks like that, except we lost a term. And so this is just that, this grand letter, but minus the first term. So n equals 0 is missing, all right? Here when n equals 0, we have p to the 0 c tilde, which is just c tilde, you know. That's just, you know, some notation. And so it's psi minus the first term, which is c tilde. So my beautiful psi is just h. You know? So the Poisson's equation goes everywhere you go. And this has been like, it's a joke for me, is that since I was a graduate student, this damn Poisson equation follows me everywhere I go. It's really strange, though. It comes up everywhere. It comes up in nonlinear filtering and control and the weirdest places, and even in fluid dynamics, apparently. I don't know. But you start with something, I guess, you know, there is something that looks sort of Poisson-like there, maybe. And then you have the standard formula here. But then a little bit of manipulation, and what do you get? What is sigma squared g? Well, remember, I only looked at positive n, but negative n is just positive n, the same thing. So it looks like gamma squared g is nothing but what? This whole thing is just the summation of x of h of x c tilde of x. You know? Which I would call, we have my notation, I'd call it pi of h times c tilde. You know, this whole thing is a product, so it's a function of x, and I'm looking at a dot product. So it looks like, so going forward in time, I get this. Going backwards in time, I get the same thing. So it looks like it should be twice pi of h c tilde, but it's not. What am I missing?